Welcome back to the deep dive. Today, we are not just looking at a research paper. We are looking at the document that effectively drew a line in the sand for modern artificial intelligence.
Yeah.
Before this paper, we were in one era, and after it, we were in a completely different one.
That's not an overstatement at all. I mean, it is so rare in computer science to have a single moment where the entire paradigm just shifts overnight. But this was it. This was one of them.
We were talking about Attention is All You Need, published in 2017. And, the title, it sounds like a minimalist lifestyle book or maybe a relationship advice column.
It really does. But instead of fixing your marriage, it kind of fixed the way machines understand human language.
The authors, Ashish Vaswani and the team at Google Brain and Google Research, they made a claim in that title that was just incredibly aggressive for an academic paper. They didn't say attention is useful or attention helps.
No.
They said it is all you need.
Right. And that was a direct challenge to the establishment. They were effectively saying, everything you're currently doing, all that complex recurrent stuff, you can stop. We found a better way.
So our mission today is to verify that claim. We've got the paper, we have the architecture diagrams, and we've got the math. We're going to deconstruct the transformer model, figure out why it basically killed off the recurrent neural network, and understand the mechanics of self-attention that power everything from, ChatGPT to Google Translate today.
Let's do it.
Okay, so to really appreciate the solution, I think we have to appreciate the problem. Take us back to, say, 2016, early 2017. If I wanted to build a machine translation system, English to German, for example, what was I using?
You were using the old guard, specifically recurrent neural networks, or RNNs. And the gold standard within that was a specific type called an LSTM, a long short-term memory network.
LSTMs. I've definitely heard of those. They were the state of the art for a long time.
They absolutely were. And they were built on a really intuitive premise, which is that human language is sequential. You speak one word after another, time flows forward. So the architecture was built to mimic that process.
So if I feed a sentence into an LSTM, it reads the first word, it processes it, and then it moves to the second, and so on.
Exactly. It maintains what's called a hidden state. You can think of it like a working memory. It reads word T, updates its memory, and then it passes that memory to the next step, T+1. It's a chain.
That seems really logical. I mean, I can't understand the end of a sentence until I've read the beginning. So what was the issue? Where did it fall down?
The issue was that computers hate sequences.
Computers hate sequences.
Computer hardware hates sequences.
Yeah,
You see, we have these massive GPUs, graphics processing units, that are designed to do thousands of calculations in parallel. They're built to process giant blocks of data all at once. But an RNN forces that GPU to act like a single human reader, going word by word.
I see. So even if I have a supercomputer, I can't process the 10th word in a sentence until I've finished processing the 9th word.
Precisely. It's a sequential dependency. You've got this, Ferrari of a processor, and you're forcing it to drive in a school zone. It just creates this massive bottleneck during training. You cannot parallelize the operation.
So training these things took forever.
Weeks.
Yeah.
Sometimes months for the really big models. But there was a second problem, which was arguably more critical for actual, intelligence.
Yeah.
And that's the problem of long-term memory, or what the paper calls the path length.
The paper mentions this explicitly in Table 1. Can you explain that concept?
Yeah.
Path length.
So imagine a really long sentence, something like, the girl who was wearing a red hat and had just come from the store where she bought 3 apples and a pear, dropped her keys.
Okay. A complex sentence for sure.
To understand that she is the one who dropped the keys, the model has to connect the word girl at the very beginning to the word dropped away at the end. In an RNN, that information about the girl has to travel step by step through every single intervening word. The hat, the store, the apples, the pear.
It's like a game of telephone.
That's a perfect analogy. Yeah. By the time the signal gets all the way to the verb dropped, the information about the subject girl might be completely distorted or just diluted. The gradient, which is the learning signal, it just vanishes as it tries to travel back through time.
So RNNs were slow to train, and they were bad at remembering things that happened a long time ago in the sequence.
Precisely. And researchers were trying everything to fix this. They were using gating mechanisms, they were using bidirectional RNNs, they even tried using convolutional neural networks, CNNs, for text.
And then Vaswani and the team come along and just say, burn it all down.
Attention is all you need. That's what they said. They proposed just deleting the recurrence entirely. No more step-by-step processing. Gone.
So instead, they introduced the transformer. And the core idea here is moving from that sequential processing to To what exactly?
To global processing. The transformer doesn't read left to right. It ingests the entire sentence at once,
The whole thing, all at once.
simultaneously. It looks at every single word and calculates how it relates to every other word in a single massive parallel operation.
Okay, that sounds a bit like magic. Mathematically, how do you just look at everything?
Yeah.
This has to bring us to the core mechanic, right? The scaled dot product attention.
This is the engine room. This is the heart of it.
The paper uses a very specific metaphor here. They talk about queries, keys, and values.
Yeah.
Q, K, and V.
Yes. And this is a concept that's sort of borrowed from information retrieval systems like old school database systems.
Okay, let's break this down because this is the terminology everyone uses now. If I'm a word in a sentence, let's say I'm the word bank in the phrase the riverbank. How do I use Q, K, and V?
Okay, so every word in the sequence gets transformed into the three different vectors: a query vector, a key vector, and a value vector. You can think of the query as the word asking a question, what am I looking for?
So bank is sending out a signal saying, help me understand my context.
Right, because bank is ambiguous. It could be about money, it could be a river. So its query vector is basically asking, are there any words nearby that clarify if I'm financial or if I'm geological?
And the keys, what do they do?
The keys are like labels on the spines of books in a library. Every other word in the sentence, the river, it holds up its key. The key represents what it defines. Here is what I am.
So the word river holds up a key that says something like geological water feature.
Exactly. And the model then calculates a compatibility score between the query from bank and the key from river. Mathematically, this is just the dot product.
And a dot product is basically just a measure of similarity, right? If the vectors are pointing in a similar direction, the number's big.
Correct. So bank, the query, and river, the key, will have a very high dot product. Bank as a query and, say, the as a key would have a very low dot product.
Okay, so I found my match.
Mhm.
The word river is the most relevant word for me. What happens next?
Now you retrieve the value. The value is the actual content, the sort of semantic meaning of the word river. And because that match was so strong, the model attends to that value. It absorbs that water geology, meaning into its own representation of bank.
So bank updates itself. It stops being just this ambiguous word bank and becomes, in a sense, riverbank.
Yes. And the crucial part is it does this for every word pair simultaneously. River is also looking at bank. The is looking at river. It's a massive, dense web of connections being calculated all at once.
That explains the attention part. But the paper is very specific. It calls it scaled dot product attention. Why the scaling? They divide by the square root of the dimension of the key vectors, the square root of dk.
This is one of those subtle but absolutely critical engineering details. So in these models, the vectors are very high dimensional, 512 dimensions, sometimes thousands. When you compute a dot product of two vectors with, say, 512 numbers each, the result can become a huge number.
Okay, so we get a really large score. What's the problem?
The problem is that we then feed that score into a softmax function to turn all the scores into a probability distribution.
Right.
And softmax is very sensitive. If you feed it a huge number, it just slams the output to 1, and for everything else, it outputs a 0. It becomes a hard all-or-nothing decision.
And why is a hard decision bad for learning?
It's all about the gradients. If the softmax curve is flat because you're way out at the extreme ends, the slope is near 0, the model can't learn. The updates stop flowing back.
It's the vanishing gradient problem all over again, just showing up in a different place.
Exactly. So they divide the score by that scaling factor to just shrink it back down into the sweet spot of the softmax function where the gradients are nice and steep. It just keeps the training stable.
It's fascinating that such a small mathematical trick can be the difference between a model that doesn't work at all and one that's revolutionary.
That's deep learning in a nutshell right there.
So we have this amazing attention mechanism. But the authors, they weren't satisfied with just one. They introduced multi-head attention.
Right. In the paper, I believe they use 8 heads.
Why do that? Is it just a case of more is better?
Not exactly. I mean, think about how you read a sentence. You are simultaneously processing grammar, tone, vocabulary, and logical flow all at once.
Sure.
If you only have one single attention head, it has to try and average all those different kinds of relationships into a single vector. It just muddies the water.
It's like trying to listen to the melody, the bass line, and the lyrics of a song all at the same time and just describing it as sound.
Yeah.
You lose the individual parts.
That is the perfect analogy. So by having 8 heads, the model can specialize. Head 1 might focus on, say, who did what to whom, the whole subject-verb-object thing. Head 2 might focus on adjective-noun pairings. Head 3 could be looking at prepositions.
So each head is looking at a different representation subspace, as the paper calls it.
Yes. They run 8 parallel attention mechanisms, each with their own set of learned weights, and then they just concatenate or stitch together the results. This gives the model a much richer, higher fidelity view of the sentence.
Okay, so we have this parallel processing machine that can understand context really deeply. But there is a giant gaping hole in this theory that we haven't addressed yet.
I know exactly where you're going with this.
If I throw the words man, bites, and dog into a bag and just shake it up, I don't know who is in trouble and who is being aggressive. The transformer, as we described it, processes everything in parallel. Does it even know the order of the words?
And the answer is, by default, no.
Right.
Not at all. To the raw attention mechanism, man bites dog and dog bites man are mathematically identical. They're just a set of words. It has no inherent concept of time or sequence.
Which is absolutely fatal for language. Order is meaning.
So they had to invent a way to basically timestamp the words before they even enter the model. And this is the positional encoding.
And this is where the paper gets weirdly specific with using sine and cosine waves.
It's one of the most elegant parts of the paper, I think. Instead of just numbering the words 1, 2, 3, 4, which can cause all sorts of issues if you suddenly see a sentence that's longer than anything you've trained on, they add a unique vector to each word's embedding. And that vector is derived from sine waves of different frequencies.
Why waves, though? Why not just have the model learn a position vector like it learns everything else?
You know, they actually tried that. The paper notes that they compared these fixed sinusoids versus learned position embeddings, and the results were almost identical.
So why stick with the waves?
2 words. Extrapolation. If you train your model on sentences that are a maximum of, say, 50 words long, and then at test time you ask it to translate a 60-word sentence.
A learned embedding for position 60 just wouldn't exist. It would be a blank.
Exactly. But a sine wave is continuous. The pattern just repeats into infinity. So the model can theoretically infer what the encoding for position 60 should look like because it follows the same mathematical function as position 50. It allows the model to generalize beyond the lengths it saw during training.
That is a brilliant example of what they call inductive bias. You're baking a useful rule into the system to help it learn more effectively.
It is. You're injecting a bit of geometry into the raw algebra of language.
So we have the word embeddings, the positional encodings, and the multi-head attention. But let's look at the full stack. The paper describes the architecture as an encoder-decoder.
Yeah, that was pretty standard for translation tasks at the time. The encoder's job is to read the English. The decoder's job is to produce the German.
Okay, let's look inside that encoder stack. It's not just an attention layer. There is also a feed-forward network in there.
Yes. So after the attention layer has mixed all the information from all the words together, the feed-forward layer processes each word individually again. It's like a digestion step. Okay, I've got all my context. Now let me just sit and refine my own meaning for a moment.
And there are these added norm connections wrapping around everything. Residual connections.
We absolutely can't ignore those. Residual connections, they come from the ResNet paper a couple of years earlier, and they're like express lanes for the gradient. They allow the learning signal to flow through the network without getting stopped or weakened at every single layer. Without this, training a 6-layer or 12-layer deep network would be incredibly difficult.
And the norm part is layer normalization.
Which just keeps the numbers stable. It makes sure that the mean and variance of the neuron activations don't spiral out of control during training.
So the encoder builds this really rich, contextualized understanding of the English sentence. Now we move over to the decoder. This is where the translation actually happens. It looks almost the same, but with a twist.
2 twists, actually. The first is that the decoder has a special layer called encoder-decoder attention.
How is that different from the self-attention we've been talking about?
In self-attention, the queries, keys, and values all come from the same place, the sentence you're currently reading. But in encoder-decoder attention, the queries come from the decoder, so the German word I'm trying to generate. But the keys and values come from the encoder's output, from the English source sentence.
Ah, so that's the bridge. This is where the German translation looks back at the English source text to decide what word it should pick next.
That's it exactly. If the decoder has just written the word dare, it can look back at the English source, see the dog, and know it probably needs a masculine noun next.
You said there was a second twist in the decoder. Masked multi-head attention. That sounds like some kind of constraint.
It is a totally necessary constraint. Remember, when we train these models, we feed the answer key into the model. We give it the full, correct German sentence from the start.
Right. For it to learn from.
But if we let the model see the entire German sentence while it's trying to predict, say, the third word, it's just going to cheat. It will just look ahead at the fourth word in the answer key and copy it.
It won't learn to translate. It'll just learn to copy-paste.
Exactly. So we apply a mask. It's basically a triangular matrix that sets the attention scores for all future words to negative infinity.
Negative infinity.
Yeah, so that when you run it through the softmax function, their probabilities become 0. Effectively, the model is blinded to the future. It can only attend to the words it has already generated.
It ensures the model remains autoregressive. It predicts the next token based only on the past tokens.
Precisely.
So that's the machine. A 6-layer stack of encoders and decoders using parallel attention, geometric positioning, and this masked learning. It's a beautiful architecture, but beauty doesn't always work. Let's talk about the results.
The results were, frankly, embarrassing for the competition.
They tested on the WMT 2014 dataset, which was the standard translation benchmark, English to German and English to French.
On English to German, the big version of the transformer hit a BLEU score of 28.4.
For listeners who don't track BLEU scores day to day, put that in context for us.
In this field, gaining 0.5 BLEU is a big deal. That's a paper-worthy achievement. The transformer beat the previous state-of-the-art, which, by the way, was an ensemble of multiple models, all combined by more than 2.0 full points.
That's a generational leap. That's not an incremental improvement.
It is, and on English to French, it hit 41.0, setting a new single model record. But, the raw score isn't even the most impressive part of the story.
It's the cost.
It's the efficiency. The paper compares the transformer to other leading models at the time, ByteNet, ConvS2S, Google's own GNMT. Those models required computation measured in exaflops. That's 10 to the power of 19 or 20 floating point operations.
And the transformer.
The base model was trained in 12 hours on 8 P100 GPUs.
Wait. 12 hours.
12 hours.
And only 8 GPUs. I mean, that's a serious gaming rig has 1 or 2. A proper research lab usually has clusters of hundreds. 8 is, almost nothing.
And that's the democratization aspect of this paper. Before this, if you wanted to train a state-of-the-art translation model, you basically needed Google-level infrastructure. And suddenly, a grad student with a modest grant could train a world-class model overnight.
The big model took a bit longer, though.
It did, 3.5 days. But still, when you compare that to the weeks or even months required for the old LSTM models, this was light speed.
This brings us right back to the death of recurrence. By enabling this massive parallelization, they didn't just make the model better, they made the research process itself faster.
That's such a crucial insight. If your experiment takes a month to run, you can maybe try 12 ideas in a year. If it takes 3 days, you can try over 100 ideas a year. The rate of evolution in the entire field just accelerated because the transformer allowed us to fail and therefore learn so much faster.
I want to circle back to table 1 in the paper for a second, the one that compares the maximum path length. We touched on this, but the numbers are so stark.
Right. For an RNN, the path length is O(n), so it's linear. If 2 words are 100 spots apart in a sentence, the signal has to travel 100 steps.
And for the transformer?
It's O(1), constant time.
It doesn't matter if the words are right next to each other or on opposite sides of a book. The distance between them is 1.
It's the difference between walking down a very long hallway to talk to a colleague versus just picking up a direct hotline. The connection is instant. And this is why transformers are so good at maintaining context over long paragraphs. They don't forget things in the same way.
This sort of leads us into a broader discussion. The paper is titled "Attention is All You Need." But is it really? Or did we maybe lose something important by killing off recurrence?
That's a debate that still kind of lingers in some corners of the field. Some people argue that by treating language as a set of words with positional tags rather than a true process unfolding in time, we lose some of the inherent causality of thought.
But the results seem to say otherwise.
The results say that for the tasks we care about, translation, generation, understanding, the global view approach absolutely trounces the sequential view.
Here's a question the authors pose right in their conclusion. They mentioned applying this to other modalities besides text, like images, audio, video.
And boy, has history proven them right on that one.
If you think about it, an image is just a grid of pixels. In a traditional CNN, you're looking at small, local patches of pixels. But with a transformer,
You can just break the image into a grid of patches, treat them like words, and apply self-attention. The top left corner of the image can instantly attend to the bottom right corner.
this is exactly what vision transformers or VITs do today.
Exactly. It turns out that attention might just be a universal computational primitive. It's a general purpose way of routing information. It's just a system for asking, I am element A. Based on my content, which other elements in this entire set are most relevant to me?
So it breaks the spatial chains of CNNs, just like it broke the temporal chains of RNNs.
Yeah, it suggests that the specific structure of the data, whether it's time or space, matters less than the relationships within the data.
I want to look at the authors of this paper for a moment. This really was an Avengers Assemble moment for AI researchers.
It really, really was.
You've got Ashish Vaswani, Noam Shazir, Nikki Parmar, Jacob Uskarate, Lyon Jones, Aidan Gomez, Lucas Kaiser, and Ilya Polasukin.
And if you track where they all are now, they are essentially the founders of the modern AI industry. They went on to found Cohere, Character.ai, Essential AI. I mean, they're everywhere.
There's a fun fact in the footnotes of the paper. It explicitly states the order of the first authors is random and all contributed equally.
I love that little detail.
He goes on to list their contributions. It says Jacob proposed replacing RNNs with self-attention. Ashish and Ilya designed the models. Noam proposed the scaled dot product.
It just shows that this wasn't one genius having a eureka moment in a bathtub. It was this synthesis of different frustrations and ideas. One person hated the speed of RNNs, another saw the potential of attention. Somebody else fixed the math to make it stable. They combined all these pieces to solve one specific problem translation, and in the process, they accidentally solved almost everything else.
Another detail from the paper I found fascinating was this idea of label smoothing.
Ah, yes, a great little trick.
They used a technique during training where they effectively tell the model, hey, don't be 100% sure of the answer.
Right, so instead of the target probability being 1.0 for the correct word and 0 for everything else, they set it to something like 0.9 and then spread the remaining 0.1 of probability mass across all the other words in the vocabulary.
And the paper says this actually hurts perplexity.
Which is a measure of how surprised or uncertain the model is. So the model is technically more confused, but it improves the final BLEU score.
Why does making the model less confident make it a better translator?
It's because language itself is ambiguous. If you force the model to be 100% certain all the time, it overfits. It becomes arrogant. By forcing it to accept a little bit of uncertainty, it learns more robust, more flexible representations. It acknowledges that there might be valid synonyms or alternative phrasings.
Arrogance leads to overfitting. There's probably a life lesson in there somewhere.
Humility is a regularization technique.
So we've covered the mechanism, the architecture, the results, the impact. But I want to leave our listeners with a final thought about the future this unlocked.
Go on.
The transformer works because it removes the constraint of sequential time. It sees the whole sequence at once.
Yes.
But the cost of that attention mechanism is quadratic. If I double the length of my sentence, the number of calculations quadruples because every single token has to look at every other token.
That is the new bottleneck. What
Yeah.
we now call the context window.
Right. In 2017, the context window was maybe a few sentences. Now with models like Gemini or GPT-4, we're looking at millions of tokens, entire books at once.
But the fundamental mechanism is still the same. It's just been heavily optimized.
So if we can eventually build a transformer that can attend to, say, your entire life history all at once, every email you've ever sent, every conversation you had, every document you've read, does the concept of forgetting cease to exist for an AI?
That is the implication, isn't it? In an RNN, memory fades over time. In a transformer, memory is just a lookup. If it's inside the context window, it is perfectly recalled. Instantly.
It shifts the entire definition of intelligence from processing capacity to something more like attention management. Knowing what to ignore becomes far more important than knowing what to read.
I think that's the perfect summary. In a world of potentially infinite context, attention really is all you need.
For anyone who wants to see this in action, I highly, highly recommend you dig up the original paper and look at the attention map visualizations they have in the appendix. Seeing the thick lines connecting a verb like making to its dependencies more and difficult, it honestly looks like a diagram of thought itself.
It's a visualization of syntax being learned from scratch. It's beautiful.
Thank you for joining us on this deep dive into what is arguably the most influential paper of the last decade.
My pleasure. It was fun.
We'll catch you on the next one.
Yeah.
Keep attending to what matters.